Alrighty, so I was actually working on yesterday's hard one, continuing it. I have some stuff, um, a lot of monotonic, stack stuff, but I didn't get anything that actually solved it. Got a fair amount of test cases, but obviously not all of them. Feels kind of bad. Anyways, let's try to do today's number of ways to assign edge weights, part 1. There's an undirected tree of n nodes labeled from 1 to n, rooted at node 1. Undirected tree, okay. So it means there's no kind of each branch is basically you can traverse it either way. The tree is represented by a 2D integer array of edges of length n minus 1, where edges at I is equal to uv, where it indicates an edge between the nodes uv. There's no cycles here because it's n minus 1 likely. Initially, all edges have a weight of 0. You must assign each edge a weight of either 1 or 2. The cost of the path between any two nodes u and v is the total weight of all edges in the path connecting them. Is the total weight of all edges in the path connecting them. Maybe there are cycles. Selecting any node x of maximum depth at maximum depth. Return the number of ways to assign edge weights in the path from node 1 to x such that its total cost is odd. Since the answer may be large, return modulo 10 to the 9th plus 7. Alright, ignore that before I forget. Okay, ignore all edges not in the path from node 1 to x. So there's one edge here. How many ways can you assign values here such that total cost is odd? So you can either only assign this a 1 or 2, so it has to be a 1. Select any node x at maximum depth. At maximum depth, I'm not sure what that means. No hint or no tooltip. Okay, so here edges are 1 to 2, 1 to 3, 3 to 4, 3 to 5. So select any node x at maximum depth. The maximum depth is 2. Oh, it's a tree. 1 is the root node. Okay, I didn't catch that. So maximum depth is all the nodes that are farthest apart from node 1. But yeah, there's no cycles here, so it's just, however, each number should have a unique value for how far it is from 1. So 4 and 5 here are maximum depth 2. So select any node at maximum depth, return the number of ways to assign edges from 1 to x. Okay, so 1 to 4 and 1 to 5, such that it's odd. So like 1, 1, no, sorry, 1, 2, 2. So 1, 2, 2 is going to give 3 and 3 to each. 2, 1, 1 will give 3 and 3 to each. I think that's the only 2 ways. Okay, yeah. Assigning weights 1, 2, or 2, 1. That's the valid number of assignments is 2. Okay. All right, it's a graph. So I think I first need to like make the graph, which is generally either 2D array or default dictionary. I'll probably do, I think it's probably going to be slightly faster if I just do a 2D array, although dictionary is pretty convenient. I guess this should probably be, graph is going to be a 2D array where the node is kind of the index, and then it gives a list. It's either going to give a list or a set of all connecting nodes from it. I'm gonna say I probably want a list. Actually, maybe I'll start with a set. Set for every index in range. Is edges. Okay, say n equals the length of edges plus 1. Edges is length n minus 1, so n is going to be plus 1. Yeah. So, and I think I need this to be, if I want to use this as one index, I would need to have it plus 1. So for everything in range n plus 1. Okay, and this is going to be the index. It's this 2D array or 2D kind of graph where the index is the node value, and that's like the first dimension, I guess, and then the second dimension is the value at that. I guess I can call this the node number, and the value at that index is going to be the set of connecting nodes. So then I'll form the graph. So for every edge, which is, let's say, n1 to n2, in the edges list, then graph at n1 adds n2, graph at n2 adds n1. So first thing I need to know is kind of determine maybe the list. It's either determine the list or the set of, I'll just say collection of farthest leaves / max depth nodes. I'll say it's going to be leaves is a set and I'll just do some sort of I'll use breadth first search, so using it by layers. Layer 1 is, or layer 0 is kind of root node, layer 1 is the children of that. So let's say breadth first search is generally using some sort of iterative stacks or queue. Probably queue or alternating stacks. I think I'll just do alternating stacks. Current is going to be node 1, and then for every, I think this might be a while true, I'll say the next level. I wish I could use next as a variable name. I'll just call it children, I guess. Children set. or children list. Children list. So for every node in the current, then I'll do guess maybe I should have a scene set as well, so it doesn't go backwards. So for every node in children, then for every kind of neighbor, I'll call it nay, every neighbor in the graph of this node, this will iterate over the set of values connected. If the neighbor is in scene, then continue, skip it. Scene adds the neighbor. Actually, scene should probably just be an array of true or false. So let's say scene is false times, it's going to be slightly faster. n+1, so I can index using just the node value. And then scene at 1 is equal to true. So if scene of this neighbor, then continue. Otherwise, scene of this neighbor is not true. And the children appends the neighbor, sure. Okay, and then if the length of children is equal to 0, then I break, in which case the current layer is the leaves. Otherwise current becomes the children. So you start with 1, children is empty, 1, every neighbor of 1, which is 2 and 3, haven't seen 2, so now seen 2, and append 2 to the list. And then do it for 3 as well. The length is not 0, current becomes the list of 2, 3, next step or next loop. The node is 2. For every neighbor of the graph of 2 should be empty, so it doesn't do that for loop. And then it does node 3, and then for every neighbor in graph of 3, 1 is already seen, 4 hasn't been seen, children appends 4, 5 hasn't been seen, children append 5, 4, 5, yeah, okay, that's it. So I'll say leaves is current, just to make sure this works. I'll just return 0 for now. Leaves is just 2. Leaves is 4, 5, okay. Okay. So now I need to go backwards, I guess. You know, I think I'm traversing backwards. Maybe I should be storing this as in some structure so that I know which layer each part of the tree is. So I know like 4 going to 3, 3 is in layer like 1. This is layer 0 and 4 is layer 2. Maybe that might be helpful. Otherwise I might get lost in terms of the leaves become the scene, and then anything that's connected to leaves has to be 1 layer less. Guess that's implied, right? If I'm going back to a neighbor I haven't seen, it has to be 1 layer up. Can't be going downwards again. Huh. How to do this? So if it was something where there was just a single kind of linkage from root to end, no branching, just like 1, 2, 3, 4, 5 in a line, I think if it's only 1, or if it's an odd number of links, then the start has to be odd, I want to say. That's not quite true. If it's 1, it has to be odd, obviously. If it's 2, it has to be even odd. Or odd even. If there's 3, if it's 1, it has to be odd. If there's 2, it's either odd even or even odd. If it's 3, odd, 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 even, 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 odd, even, even, odd. Right. There has to be an odd number of odds, right? There has to be an odd, needs to have odd number of odds. Alright, needs to have an odd number of 1s in the path. Can have any number of evens as long as that's the case. So it's either like 1 odd or 3 odds or 5 odds. Okay. I guess. Guess I can maybe do something where it's just pushing down all the ways to get to a particular node as even and all the ways to get to a particular node as odd, and then just do a calculation based on that. That might work. All the ways to get to a particular node with even, all the ways to get to a particular node with odd. I mean, it's probably not that big a graph, right? It's kind of a big graph, 10 to the 5th. Do I need to time, should I only do backwards tracing? Like, once I know the leaves, should I only go backwards up the branches? Back to root 1? Because if I start from root 1, I would, in theory, be going down to 2 and 3, and then going down whatever branches down 2, but then there might not be anything there. That's worth considering. So I go upwards from the leaves, it's less computation, I think. Can I just start with 1? Like one way for the 4? Is that gonna work? Because it's all multiplication, yeah. Because, so 4, actually, how does that work? So there's one way to get to 3 with odd, one way to get to 3 with odd. Does that count as, how would I count that? Alright, let's try something. Let's say it's like 1 to 2 to 3 as the nodes here, and 1 to 4 to 5 here. So how would this count out? Actually, maybe this is a little too easy. Maybe 1 to 2 to 6 here, and then 1 to 2 to 4 to 5 here. So 5 and 6 are the leaf nodes at maximum depth. So I would say that 5 and 6 gets processed. Then I would say there's one way to get to 4 where there's an odd, and one way to get to 3 where there's an odd. Like, what does that mean exactly? So if the total branch is, if the total thing here is odd, then 4 to 5 has to be even. No. I think I need to not worry about 1 or 2, it's just odd or even, right? It's just the parity. So I'm thinking about the linkages, right? So there's 3 links here and there's 3 links here. So if this is an odd link, then these two have to have one odd link in them. Alright, let's go ahead and try this test case at some point. So 1 to 2, 2 to 3, 3 to 6. Also 2 to 4, 4 to 5. I probably should solve this too. Okay, so if this is odd, say this is odd, this means that these two have to both be odd, or these two have to both be even. So there's one way to get to here with odd and one way to get to here with even. Same thing here, there's one way to get here odd and one way to get here with even. And then from here, what does this mean? So 4 connects to 2. So if 4 has one way to get here with even, then to 2 there should be one way to get to 2. No. Let's see. So the number of ways to get to here with even plus the number of ways to get to odd, right? Because if this is even here, then making this even would make this an even. And if it's odd here, making this odd would make this even. So there's like the total number, the sum of the number of ways to get to here with even and odd. And then to get to 2 with odd, isn't that also the sum? If it's even, it has to be odd. If it's odd, it has to be even. Am I thinking about this wrong? Am I supposed to be focusing on the edges rather than the nodes? And I might focus on the edges. How would that even work? If I focus on the edges, odd, even, odd, even. So if I make this even, this becomes, if assuming 4 is odd, or the path all the way to 4 is odd, then if I make this even, the path to 3 has to be odd. And if I make this even, the path to 3 has to be. Oh, sorry, that's what I said before. If the path to 4 is odd, I make this even, then the path to 3 has to be odd. If I make this odd, the path to 3 has to be even. I'm probably overcomplicating this. The cost of the path between any two nodes is the total weight of all edges in the path connecting them. Select one node. Select any one node at maximum depth. Return the number of ways to assign edge weights in the path. I am just returning the sum of all of it, right? Ignore all edges not in the path of node 1 to x. Right. It doesn't actually say like find the total number of ways to assign the weights. So the answer select any node, return the number of ways. Select any node x at maximum depth. Shouldn't this be select all nodes x? Like for all nodes x, they need to be assigned such that assign weights in the path such that the total cost is odd. It's just a poorly worded question, I think. The cost of a path between two nodes is the total weight. Select any node x at maximum depth, return the number of ways to assign edge weights in the path. It's like for all x at maximum depth, the path from 1 to x must be odd. How many ways can there be to assign those weights? Does linking actually work? Okay, let's just do something simple, like it's really simple. 1 to 2, and 1 to 3. So there's only one way here. Right? This is odd and this is odd. Okay. So let's say 1 to 3. Let's say it's 1 to 2 to 4 and 1 to 3 to 5. In which case, like there's 2 ways here and there's 2 ways here, so it's 4. One to 2, 2 to 4, 1 to 3, 3 to 5. I assume this is going to be 4. Be even odd or odd even. And then same thing, this could be even odd, odd even. 1 to 2, 2 to 4, 1 to 3, 3 to 5. There's only 2 ways. And number of ways to assign edge weights. 1 to x. Oh, is x? No. Select any node x at maximum depth. Return the number of ways to assign edge weights in the path. Oh, is it the same for every single thing? Oh, it is the same for every single thing, isn't it? That's what they're asking for. It's just the length of the thing. Why would it be a large number then? Any two nodes UV is the total weight of all edges in the path connecting it. Select any nodes at maximum depth. Return the number of ways to assign edge weights. Okay, let me do a test case here. So this was 4, huh? 1, 2. So the maximum depth here was 3. And the answer was 4, which was the same as like these 4. Okay, I have a suspicion that this is just strictly based on the length of the longest thing. So let's extend this to become 5, 6, in which case it is a 4 length depth. And with 5, 6, 4 length depth, so it's either 1 or 3 odds within the length. 1 or 3 odds, so if it's 1, then it's 4 choose 1, and if it's 3, then it's 4 choose 3, in which case it's still just 4 plus 4, which is 8. So I think this is 8 for case 3. Cycle detected. Really? Did I make a cycle? Oh, whoops. Yeah, I did. I did. Yeah, it's 8. Okay. So I just need to know the maximum depth, I guess. And then, so I think I increment this depth each time here. Let me go ahead and print out the depth here. I think this should print out 4. Print out 4 depth, okay. And then, probably should keep it. So the answer should just be the number of ways to do it. So I guess this could be a pretty big number, huh? 10 to the 5th, because it'd be 10 to the 5th choose 1, 10 to the 5th choose 3, 10 to the 5th choose 5, all the way, or depth choose 1, depth choose 3, depth choose 5. Probably some fast calculation here. Alright, so let's go ahead and just do some math, I guess. So I need to do the summation of like sum of d choose NCR of the depth choose 1 or odd for every odd in range from 1 to depth, incrementing by 2, right? So the depth choose 1, depth choose 3, depth choose 5, depth choose 7, all the way up to depth choose either depth or depth choose depth minus 1, 1 or 2. So let's say depth, let's say it's like 10, 10 choose 1, 10 choose 3, 10 choose 5, 10 choose 7. I need to do this quickly. Because this thing is a pretty big number, 10 to the 5th. I need to do this like in n time. Probably. Okay. So 10 choose 1 is going to be 10 factorial over 1 factorial, 9 factorial. 10 choose 3 is 10 factorial over 3 factorial, 7 factorial. And then 10 choose 5 is 10 factorial, 5 factorial, 5 factorial. 10 choose 7 is 10 factorial over 7 factorial, 3 factorial. And then it kind of does the reverse, right? It's kind of the mirror. It's going to be mirrored if the depth is even. It's not going to be mirrored if the depth is odd. I guess if this was 11, then it'd be 3, 8. If this was 11, it'd be 3, 8, and then there'd be like 7, 4, 9, 2, 9, 2. So I don't think I can rely on it being mirrored. Choose 1. I can't do 10 to the 5th factorial either. What was the simplification for these factorial calculations? I forget. There's like this really famous formula for calculating what was it? Fast calculation of combinations in Python. I don't think this is what I want to search. Not really it. This is fast for a single calculation, but this is not that. Given an arbitrary n value, is there a fast way to compute nc1 plus nc3 plus nc5 plus dot 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 nc k, where k is the largest odd value less than or equal to n? Alright, fastest sum of all combinations for any positive integer n is always exactly 2 to n minus 1. Sure, that's fine. That's like Pascal's triangle, kind of. So, according to binomial theorem, the sum of all combinations for given n is 2 to the n. Okay, so we split it up into the fundamental property of combinations that the sum of the even index combination equals exactly equals the sum of the odd index combinations. Is that true? Really? Sum of the even combinations. Isn't that assuming n is like odd or even? So, because, now why is that true? I mean, I guess it's, what, there's not the same number of terms. No, what if there's like 1, 1, 2, 1? Yeah, 1, 2, 1 does work. And then 1, 3, 3, 1, 1, 3 equals 3 plus 1. Huh, I never 1, 4, 6, 4, 1, 1 plus 6 plus 1 equals 4 plus 4. Whoa, I did not know that. Okay, so it's just 2 to the power of the depth divided by 2. Yeah, I guess take it to the modulo. Wow, that's pretty mathy right there. Oh, come on, man. What? How is it even that slow? I guess I, okay. I guess I don't need to do all this jazz for finding a graph, because I just need to iterate downwards. You need to form a graph. I wonder if I can. Okay, so let's think about this. Let's create a set for every node. Do you think I need both ways? I assume it doesn't always go from lowest to highest with a graph. Create edges. Leaves is a set. I don't need that. I just need the children, right? Current is 1. Seen as false. Depth is 0. Children is empty. For every node in current. For every neighbor in graph. I think maybe I should probably just remove. Yeah, maybe I can just not have seen. I can actually do a removal of the current node from the list of its neighbors. For every node in current, so starting with 1, for every neighbor of current, I can just say graph this neighbor dot remove this current node so it doesn't go backwards. Then I don't have to do the scene. Then children add the neighbor. And length of children is 0 break. Current equals children depth. Okay, I think that's fine. That should speed things up. Scene is no longer needed. Looks like it's doing infinite. I guess I didn't remove it correctly. Yeah, it's going infinite. For every node and current, for every neighbor. Whoa, what happened to the removal? Whoops, I removed the wrong thing. Removed the wrong line. Okay, that should be faster. Just need to, guess I can probably just remove this line. 10 to the 9th plus 7. Anything else here? I think I do need to form the graph. I don't think there's a way to skip this part. Ref search. Yeah. Going pretty slow, it looks like, for some reason. How odd. It's even going slower than before. Yeah, just a small question is set remove faster or slower than set discard in Python. Have identical performance when the element exists. Discard is faster if you need to handle cases where the element might be missing. Okay. Do, 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 do. How would I make this faster? I go down. For every node, create a set. For every n1 to n2. Ref first search. 2 to the power of depth divided by 2. I guess this is the same thing as 2 to the power of depth minus 1, right? I wonder. I wonder if this is what's slowing it down, to be honest. Okay. I think this is the calculation that's slowing it down because def could be a really big number. Right. So what is the way to make this faster? 2 to the power of a large number modulo. Okay. Two to the power of n minus 1, where n can be large, up to 10 to the 5th, then returning in mod 10 to the 9th plus 7. I'm guessing the speed is slowed by the exponentiation calculation. What is the faster way of doing that calculation in mod? Ways to compute using the Python's built-in 3-argument PAL base. Oh, POW base. I think I've done this before, and I probably also made this same mistake. POW base 2 depth -1, and then the base is 10 to the 9th plus 7. Close. That's even slower than before. POW base, instead of computing the massive number first and then scaling down. POW 2 n 10 to 9 plus 7 performs a modular operation at each intermediate step using binary exponentiation algorithm. This keeps the integer small, prevents memory bloating, drops exponential time complexity to a blazing vast of log n. That still is not very fast, so it's the correct value, but it's not very fast. For microseconds, I did not see much improvement. I did not see any improvement so far. Technically, the first one was even faster, even when I was using the scene array. What is going on here? Tempted to just call it a day. Graph. I mean, indexing into a 2D array seems pretty darn fast. Default dictionary seems slower than that. Creating the graph from the edges. That seems okay. Not sure how you'd go around doing or not doing that. Current is 1. I mean, I guess I could use a queue here rather than alternating arrays. The queues, can't see why a queue would be faster. See why a queue would be faster. Okay, I guess one final question. Fastest way to determine the max depth of a binary tree given 2D array of index equals node and value at the index equals list of neighbor nodes. I assume it's breadth first search, but is there a faster way? Is it depth first search? Iterative depth first search using a explicit stack or highly optimized recursive depth first search. So it has the same theoretical time complexity of O of n, but breadth first search is slower. Memory overhead, buffer search stores entire level of nodes in a queue at the same time. Balanced tree. Iterative depth first search. Max depth first search. So iterative is just non-recursive. So handle the deep trees without hitting recursion error. If the node has no neighbor, it's a leaf. So max depth equals depth, else slightly cleaner, very fast. Okay. Milliseconds, adjacency darkness, ensure your neighbor list only contains children nodes directed downwards if the array contains undirected neighbors pointing back upwards. You must pass a parent tracking variable to avoid infinite cycles, which will slow down execution. Guess I just need to understand why this is faster. Seems like it's going down every path. Yeah, well, I did mean to say that it's going down every path in both buffer search and depth first search. Keeps memory tight, scatters memory. Depth first search uses a PRC array. Hardware, memory layouts, and data structure overhead. I guess it's true that here it does use stacks or lists each depth, which can grow kind of large. So let's see. Stack start 1. Pop the node for every neighbor if the depth is less than or equal to max depth. So update the max depth if it's higher. Otherwise, go to its neighbor on the stack, or stack appends it. Okay, I guess I'll try to do this. Okay, so same deal though, just need to calculate depth. Determine depth to farthest node, leaf using iterative depth first search, which is supposedly much faster than ref first search. So current equals 0, current node is 1, depth is step starting at 0, I assume. And this is a stack. So while there is something on the stack, node equals current pop, and then I guess it needs to store the node, probably needs to store the node and the depth of this node. So node and, okay, this should be max depth. I'll just call it D. node pop, and then for every neighbor in the graph of this node, I'll remove this node from this graph, this neighbor, so it doesn't cycle back. And then I'll do, I guess I should call this the stack instead of current. And then stack appends the tuple that is this neighbor node and the def being d+1. So the stack has tuples of the node value and the depth of the node. So there should be an if here. Yeah, it should be an if. If there is nothing in the graph of this node, so there's no neighbors, then I think there's just nested if statement here. Yeah, if this current def is greater than max depth, then max depth updates, else it iterates over its neighbors. And then what? And that's it, I think. Okay. Which one? Oh my god. Oh god damn it. Alright, I'm done. So done. I guess I can keep this thing. Alright, so this is the thinking work behind math logic. I'm actually really not sure how these guys got so much faster than me. I am just amazed and also too tired. Alright, summary. So I'll say this is kind of a weird problem that fundamentally is can be solved by finding the maximum depth of the leaf nodes. Maximum depth, i.e. path length of path to leaf nodes, to farthest leaf node, I guess. Still couldn't find a way to make this fast. Stumped. So the reasoning for why this calculation, or the reason why this value, the max depth value, is needed is because for any given longest path length, the number of odd weights within it needs to be odd itself. So for example, if the longest kind of length is 5, or let's say 10, the weights, the way to assign weights would be to assign 1 odd, 9 even, or let's say 1 odd, 9 even, 3 odds, 7 evens, 5 odds, 5 evens, etc. Since you need to have an odd number of odd weights so that the total sum itself is odd. Like, it's pretty straightforward kind of number theory. Not even number theory, really. Kind of just basic patterns of odds and evens. Thus, the number of weight, or for calculating the combinations of such, it would be 10 choose 1 plus 10 choose 3 plus 10 choose 5 ... plus 10 choose 9, where of the 10 kind of links or edges, choosing some number of them to be odd using the help of powerful AI. It allowed, or it suggested, or it told, it said that that value, that sum, is equal to 10 to the, or 10 to the n, or 2 to the power of n, sorry, 2 to the power of 10 divided by 2, since the sum of n choose k, the sum of n choose k, or let's say n choose e, where e is any even number less than or equal to n, is equal to the sum of n choose odd, where odd is any odd number less than or equal to n. I guess this makes sense, given kind of Pascal's triangle / binomial theorem. All right, anyways, I used depth first search, or I used breadth first search, and then tried depth first search to find the max depth. Use the formula, which is going to be 2 to the power of n divided by 2, which is the same thing as 2 to the power of n minus 1 in the mod. And yeah, all right, whatever. Time complexity is going to be O of n, since either breadth first search or depth first search will go through, actually maybe this should be n plus e. We'll go through O of n to go through every node to find the maximum depth, and generating that 2D array, 2D graph array, is O of e going through all edges. I guess O of e is still O of n, because O of e in this case is n minus 1, right? Or e is n minus 1. space complexities can be O of n, since the graph needs to have kind of n size to have all the nodes. All right.